So we're going to continue with chapter 6. We're going to look at nucleophiles and electrophiles and the arrow pushing that describes their reactions. So let's look here. So these are going to be polar reactions because nucleophiles and electrophiles, by definition, are polarized. The nucleophile is going to bear a negative charge or a pair of unpaired electrons, or it will bear a center of high negative charge density. The electrophile will have an empty orbital or an empty low-lying orbital, or an area of high positive charge density, so that the nucleophile will attract the electrophile and vice versa. So these are going to be polar reactions. They'll involve ions as reactants, intermediates, or products. The negative charges will be attracted to the positive charge. Electron-rich species are attracted to electron-deficient species. And these are the electrostatic potential diagrams of methyl chloride and methyl lithium, where remember that the red shows the high density of electrons and the blue shows the low density of electrons, or high negative charge and high positive charge, high positive charge. So nucleophiles can donate a pair of electrons. They are Lewis bases. The more polarizable nucleophile will be a stronger nucleophile, and that will become important in the next chapter. You will have to know that in the next chapter. Also, the less stable nucleophile will be a stronger nucleophile. Remember that stability and reactivity are inversely related. So a nucleophile that is less stable is more reactive, as in any other situation. So here is ethoxide, OET. This is the methyl anion. So these are both anions. They're going to be more reactive than these neutral molecules, ethanol and 2-butene. And those were all, let me go back, these are all examples of molecules that have pairs of electrons that can be donated. Here the pair of electrons is in the carbon-lithium bond. Here the pair of electrons is a lone pair on oxygen. Lone pair on oxygen, the pair of electrons in the pi bond will be the ones that are donated here. So the electron-deficient species can accept a pair of electrons. So, for example, the carbocation can accept a pair of electrons into its empty p orbital. The way this is drawn, it doesn't look like it's empty. This should really be a dashed line because this orbital is empty. Once again, a less stable electrophile will be a more reactive electrophile. Now here, this is actually a neutral molecule, but this has a highly polarized bond so that the carbon has a partial positive charge and the chlorine has a partial negative charge. So you'll need to be able to recognize this. Anytime you have a carbon attached to a heteroatom, that means an atom other than carbon or hydrogen, it's going to be polarized, either partial positive or partial negative. Nucleophiles and electrophiles. So here's an example. This is from your textbook. Label all of the nucleophilic and electrophilic sites on the following molecule. So remember, what I just said is that anytime you have a carbon bearing a heteroatom, here's a carbon bearing a heteroatom, you're going to have a reactive site. But now here, this one is going to be a little bit tricky. I urge you to go in and work this problem because this pair of electrons can be donated in, form a carbon oxygen double bond, and this pair of electrons comes out, and the carbon here is going to be bearing a negative charge. So this carbon, even though it's not bonded to a heteroatom, it's sort of attached to a heteroatom through a resonance structure. So it will be reactive because of its relationship to that heteroatom. Here are some common nucleophiles, some common electrophiles. Remember the electrophile nucleophile guide that I have for you over in the bookstore. You might decide that it's going to be a good investment now that we are going to be covering electrophiles and nucleophiles. And in some cases, I'm going to point out some deficiencies that are actually in your textbook because of the typesetter's requirements. Some of the arrows are drawn incorrectly, and I'll point that out to you in just a minute. So here you can see the carbon is bearing a partial negative. Here oxygen is high in electronegativity. It's second only to fluorine, so it has a partial negative charge. And this, once again, has, even though it's not polarized, it has a pair of electrons in the pi bond, the pi electrons, that can be donated and can function as a nucleophile. Here, these are electrophiles. The carbon is bearing a partial negative charge because there's a through bond interaction, carbon-chlorine, through bond interaction where chlorine is pulling electron density onto itself because it's high in electronegativity. And so the carbon, as well as these three hydrogens, are all bearing a partial positive charge. And here, this would be after a leaving group has departed, this carbon is bearing a full positive charge. So this is obviously going to function as an electrophile. Now, the mechanisms and arrow pushing. So here, this is the beginning where I'm going to be pointing out instances in which the arrows are drawn just a little bit wrong. In some cases, going to be confusing perhaps. But I have to say, this book does a far better job than most. Okay? So, here you have the arrows, it says recall the use of these arrows in the acid-base reaction. So here you have a base, B, that is not boron. B, when you see the double dot, that's base, not boron. And so the pair of electrons is going to deprotonate the acid. So it comes in, it bumps into the proton and leaves with the proton. It picks up the proton. And so this proton is now attached to that pair of electrons instead of this pair of electrons. And A minus is deficient in electrons. So what I was talking about is this, remember how I talk about the reaction needs to occur through the antibonding orbital. And so the antibonding orbital, for this bond, there's going to be one out here and there's going to be one back here. And this arrow, if it's drawn properly, it needs to show that pair of electrons coming in and populating the antibonding orbital. So it would come in and it would actually come straight in at the hydrogen, not off at an angle. It should just come straight in here. And so this pair of electrons occupies the antibonding orbital, and so that's what I'm talking about. So the pair of electrons comes right into hydrogen and comes straight in. So it will come straight in on the same line parallel to the line representing the HA bond. four main ways that electrons can move in polar reactions. So, first, nucleophilic attack. That's going to be the most common one. Then loss of a leading group. That's going to be, I would say, second. Then you have this acid-base proton transfers. In your textbook, this is called proton transfer acid-base, but I've moved it up to the front, and you'll see why in a minute. And then there's rearrangements. We're going to discuss all of those, and you're going to have 2 or 3 slides for each one of these to describe and detail exactly what each one is. But here there's a nice list, and I've moved this up because this way you can remember it as NLAR, N-L-A-R, nucleophilic attack, loss of a leading group, acid-base proton transfer, and rearrangement. It might help you to remember it if we have this nice little acronym here, NLAR. Nucleophilic attack, loss of a leading group, acid-base proton transfer, and rearrangements. Nucleophilic attack, that was number 1 in NLAR, remember? So here we show it's very simple, bromide coming in, the pair of electrons is going to occupy this empty orbital. So the pair of electrons comes in and attacks at carbon and forms a carbon-bromine bond. So the tail of the arrow starts on the lone pair, and it moves over. It shows the way that bromide would need to move, actually, and it points at the head, actually, should occupy the antibonding orbital, or the empty orbital. Antibonding orbitals are always empty. So the pair of electrons occupies this empty orbital that is residing right there on carbon. The electrons are shared. They form a new bond, and the electrons aren't actually transferred. You have a new bond formed here. Now, nucleophilic attack can require more than one curved arrow. So here, what you're doing is the pair of electrons on oxygen, the non-bonding pair, needs to occupy the antibonding orbital of the bond that's being broken. The bond that's being broken is the pi bond, and the antibonding orbital is down here. So this is not actually going to come up here and attack. This would be more like it's occupying the antibonding orbital of the carbon-chlorine bond. So that makes no sense. So this really should come down and point straight up that carbon-oxygen bond, and it will occupy the antibonding orbital that's right there. And if you want to see a good example, here you can look at the nucleophile electrophile guide, and you can see the way that that arrow is coming right up and showing that the electrons have to occupy the antibonding orbital. So it's correct there, it's not correct here. And so I think you can memorize this, but from my perspective, it's always easier to remember if you understand what it's supposed to be doing. And then when you see the arrows drawn a little differently later on, you'll know whether it's significant or not. Because right now, you wouldn't understand why the arrow comes in from the side, and then sometimes from the bottom, and then sometimes the other side, etc. And they're all wrong except when it comes straight in from the bottom, okay, on the same line as the carbon-oxygen bond. The alcohol, the nucleophile, attacks a carbon with a partial positive charge. This is going to have a partial positive charge because carbon is bonded to oxygen. Oxygen is electronegative. Oxygen will be withdrawing electron density from carbon, and it has a pair of pi electrons, the pi bond, and pi electrons are more loosely held, and they are more polarizable, and so the the sigma electrons will be drawn up towards oxygen, but the pi electrons will be drawn towards oxygen much more. And so this bond is highly polarized. There will be a significant partial positive charge on carbon. There will also be a partial positive charge because of this carbon-chlorine bond. So that carbon is bearing a pretty good size positive charge. So the pair of electrons comes in, and now the way that it's drawn, if you want to show it as attacking this resonance structure, oxygen just comes in and attacks straight at carbon bearing the positive charge. And so this structure is the same as that structure. Notice that it's drawn as an equilibrium. So you could have this alcohol molecule coming off, and the pi bond, the carbonyl pi bond, reforms. So this is an equilibrium. It has a low energy of activation. So that's still on the nucleophilic attack. More nucleophilic attacks. So here, some pi electrons in benzene will attack its sulfur, and the pair of electrons moves up onto oxygen. Sulfur is obviously going to be bearing a fairly large partial positive because the sulfur is attached to 3 oxygen atoms. And so now, since the pair of electrons moved out and onto sulfur, this carbon atom will be electron deficient and bearing a positive charge. Loss of a leaving group. Remember, NLAR, N-L-A-R. So now we're on the L, loss of a leaving group. The heterolytic bond cleavage, an atom or group takes the electron pair. Here it is, you have bromine leaving and taking the pair of electrons that's in the carbon-bromine bond with it. So bromine will leave with a negative charge. This will be bromide surrounded by 8 electrons. So up here it's 2, 4, 6, 8, where one pair is shared. Now it's 2, 4, 6, 8, but none are shared. This is bearing a negative charge, that's bearing a positive charge. It's common for more than one curved arrow to be necessary to show the loss of a leaving group. So, especially if you have resonance structures drawn. Electron density, remember this is just one of the resonance structures. You could draw a resonance structure where you put a pi bond here and push the electrons down and have a negative charge right there on this carbon instead of on this oxygen. But this is the most stable of the resonance structures, and so often this will be the one that's given, not the one that facilitates drawing the smallest number of arrows. So here we draw, 4 different arrows just to get us really from one resonance structure to the other. And then you see chloride leaving, and when it leaves, it will take that pair of electrons with it, and it will bear a negative charge. This then will be a neutral molecule, but it will just have charge separation at one of the NO bonds. Proton transfers. So remember, this is where I substituted the acid base. NLAR, N-L-A. So this is the acid-base proton transfer to 2 curved arrows. So here we have the carbonyl non-bonding pair picking up the proton. Okay, so this is going to bump into a proton, abstract the proton, the pair of electrons in the hydrogen-oxygen bond moves back onto oxygen, satisfying the positive charge. So oxygen of water, and it's not even drawn here, the oxygen of the water will be neutral now, and water will depart as a neutral molecule. Here, in this case, water isn't even shown, so use you simply draw one of the arrows, pull the electrons back onto oxygen, and so now the oxygen is no longer bearing a positive charge, and the proton, it's just drawn as just leaving, and it's drawn in as minus H plus above the arrow. You often see this. So this is really the same as that. When you have a proton leave, it never just leaves as a bare proton. You'll always need something to pick up another proton. It could be a molecule of solvent, it could be a reactant, it could be a product, but protons don't just float off by themselves because it would be too high in energy. They're attached to something. More on proton transfers. So here you have hydroxide abstracting a proton. The pair of electrons moves in and forms a carbon-carbon double bond. Here you can see the double bond forming. And the pair of electrons moving out onto oxygen. Oxygen is going to bear 1, 2, 3, 1, 2, 3 lone pairs and bear a negative charge. You can also show it, it's totally acceptable to show it as a proton hydroxide abstracting a proton and the pair of electrons moving in and residing on carbon. So this would be C minus right there. So it would simply be C minus. And then these are two different resonance structures of that anion, where the pair of electrons moves in and the pair of electrons moves out onto oxygen. And so this resonance structure is going to be the greater resonance contributor because the negative charge is on oxygen, which is higher in electronegativity rather than carbon. Now, let's talk about rearrangements. Carbocations can be stabilized by neighboring groups by slight orbital overlapping called hyperconjugation. And so here you have this, remember this is empty. When you have a positive charge, this is empty, that's empty. And you can have the CH3, remember it's rotating like a propeller, and it can line up so that one CH bond is more or less parallel to the empty p orbital. And when that happens, some electron density in the CH bond can be donated into the empty p orbital. And so that's what is being shown here, is some electron density being donated. It's a stabilizing effect. It stabilizes this C plus a little bit and spreads some of the positive charge out, because now this carbon will also bear some positive charge, and so will the proton. And this is called hyperconjugation. You remember what conjugation is. Conjugation is the overlapping of pi bonds that are next to each other. And so you see that here, that's what's happening, is the pi system is overlapping, and here the pi, quote, system is just an empty p orbital, is overlapping with this CH bond. But when this happens, the conjugation is much less, and so it's called hyperconjugation. In chemistry, anytime you see this word hyper, it means that it's sort of a lesser effect, and it will be observed on, in addition to other effects. It will be observed on top of or over other effects because it'll be a secondary effect. It's because it's so much less. So that's what the word hyper means. Now, hyperconjugation explains the carbocation stability trend below, and you will need to know this very, very easily. So, if you don't already. So, what it is as you increase the number of substituents on a carbocation center, it's a stabilizing effect because the positive charge is being spread out, spread out, spread out. And remember, anything that you do to spread out a charge stabilizes the system. So methyl, the charge is not spread out at all, and you go over here to this tertiary carbocation, and the charge is significantly spread out. So here you're increasing the stability as you increase the substitution. More on now. Now we're getting the actual rearrangements. That was just helping you understand some information you're going to need for these rearrangements. Now, the two very common types of rearrangements are called the 1-2 hydride shift, where H is moving, it's migrating from the 1-2. It's migrating one position over. So this would be carbon 1, that would be carbon 2, or position 1 and position 2. And it's migrating with its pair of electrons, so it's migrating as an H minus. So it's called hydride. Now, in this one, you have CH3 down here, and CH3 is migrating, again, from position 1 to position 2, so it's called 1-2. And this is here, they're calling it a methide shift. Most books call it a methyl shift, 1-2 methyl shift, because methyl is shifting from position 1 to position 2. So now you see the CH bond started over there, now it's here. The methyl group started over there, now it's over here. It only shifts one position. It doesn't ever shift like 2, 3, 4, 5 positions over. Just next door. It just goes next door. And it only moves over if it creates a more stable carbocation. So here, this carbocation has 2 substituents attached. Now over here, this has 3 substituents attached. So remember what we just saw on the previous slide, the more substituents, the more stabilization. Here, once again, this carbon atom has 2 substituents. It's rearranging to a carbon atom that has 3 substituents. This one is more stable. It's going from a secondary to a tertiary carbocation. Secondary carbocation because it has 2 substituents, to a tertiary carbocation because it has 3. Secondary, tertiary. And one last thing. You might have a question. Does this ever happen with ethyl or propyl or, say, T-butyl? Yes, there have been studies on that, and yes, it does happen. But as you increase the size of this group, it reduces the rate greatly. So the rate of a 1-2 hydride shift will be greater than the rate of a 1-2 methyl shift. And that will be greater than a 1-2 ethyl shift or a 1-2 propyl shift. Because think of it like this. Here, what's really doing the migrating, what's attracted here, is the pair of electrons in this double bond, in this carbon-hydrogen bond. And so what's happening is the pair of electrons is moving over, and it's dragging the proton with it. Now the pair of electrons is moving over, and it's dragging the methyl group with it. Well, as this group gets bigger, the pair of electrons is having to drag that whole group over, and it just gets it gets harder as this group gets larger. So it's much less likely to migrate an ethyl or a propyl or a butyl. So these small groups are the ones that are most often seen. And also, if you have a situation like here, you might ask, well, why didn't the methyl group migrate? Because the smaller groups will migrate more rapidly and they'll be more likely to migrate because the pair of electrons in the bond only has to pull with it a proton. If this were to migrate, it would have to move a whole methyl group. So the CH migration, that 1-2 hydride shift, is favored over the 1-2 methyl shift. Combining patterns of arrow pushing. So now we see the combination of the NLAR. So all of those. So now we see, remember this is the A, acid-base proton transfer. The pair of electrons is attacking the proton, abstracting the proton, and it doesn't even show minus Br minus down here. It just shows it's picked up a proton. Now oxygen is bearing a negative charge, bearing a positive charge. Then you have the pair of electrons in the carbon-oxygen bond moving off with oxygen. So oxygen departs as a neutral atom. So this the loss of water. Water will leave as a neutral molecule, and now this carbon atom will bear a positive charge. So this is loss of a leaving group. NLAR, this is the L of LAR. So now we have a carbocation rearrangement, the R of the NLAR. So here we have a methyl shift. The pair of electrons in the carbon-carbon bond is being attracted to this positive position, and it drags with it that methyl group. And so the positive charge goes from a secondary carbon to a tertiary carbon. So that's the driving force. You're going to a more stable carbocation. And then last, we have nucleophilic attack by the bromide. The bromide picked back up from over here where it was lost. You have nucleophilic attacks. The bromide shows up here at the carbon that was bearing the positive charge. So, N, L, A, R. That has an example of each one of the NLAR rearrangements. Two of the patterns can occur in a single mechanistic step. Okay, nucleophilic attack and loss of a leaving group. These are the most two common steps of the NLAR. That's it. So next, we'll in the final section of chapter 6, this will be sections 10, 11, and 12. We'll look a little more at some of the nucleophiles and electrophiles and their reactivities.